Greetings, my name is John Gabriel and this is the new Calculus channel. So today I'm going to talk about a topic that I've talked about many times before, but in a little more detail and again from a new perspective. And I'm also going to focus on how someone with a purported master's degree from a public education in Sweden actually thinks. So let's begin. Now, so OnSite Math, and I'll give you the link to this discussion. We see that I'm throwing a challenge here by this academic from Sweden telling me that there are no valid real numbers. Okay, this guy, first of all, is a complete idiot and has no clue about anything in mathematics. He's never done a proof in his life. He doesn't understand the concepts. His grammar is poor, and his communication is pitiful. It leaves much to be desired. But in any case, so he lists 3 PDFs here, and so we get into the discussion, and I explain to him that the PDF is written by R.D. Arthon, and it's based on the ideas of Eudoxus. He later twists this to say that the construction was by Eudoxus, but that's not what I said. So in any case, we move along here, and we see the discussion continuing, and somebody intervenes here, a guy called timba@gmail.com, Timothy Golden, okay? And he says, well, I think it's down here somewhere where he says, how do you multiply, for example, 2.1 by 2.2 or something like that, right? So in any case, and then what I do is I write a complete answer to that question, and so where do I answer that? I'm trying to find that now. I should have found it already, but okay. So I know that my answer is right at the end. So if I go right down to the end here, that's all that matters here. Here's the answer in this comment here, and I'll place a link to this particular comment so that you can see it. So you don't have to read all the other garbage, but you can if you want to. At any rate, so we reach a point where Zelos Malem, this is my opponent, so to speak, tells me that you can define multiplication as he's done here. Now notice in this second step, he simply assumes that A times C is AC. And so I told him that that's not valid, because if you're going to be defining multiplication, you need to explain how it is defined generally for all numbers, okay? Not only for integers, etc. So what he does is he simply says that AC is equal to A times C, which is A times C, and he later says that everybody knows that. But, you know, that's incredibly funny, because I gave an entire description here of what multiplication is exactly in geometry, okay? And so without further ado, I'm going to show you very quickly what happens in geometry. So in geometry, we have subtraction and addition defined without numbers at all. And this happens from the realization of requirement 2, which is not an axiom, by the way. There's this myth that their mathematics has to be based on axioms. Well, thankfully, my ancestors didn't think like the morons of the last 400 years or so. But the operation of difference or subtraction is realized from requirement 2 of the 5 requirements, not axioms in Euclid's Elements. And if a line can be extended, then it can also be reduced or diminished. So if extended, then the extension is called a difference. If extended, then the new distance of the line is called an addition. So if you just look at the extension, which is this pink part here, that's a difference. If you look at the whole part, that would be the addition. So you've already got addition and subtraction defined without numbers, okay? Now, the same thing happens with division and multiplication. You define them using the geometry of a circle. In particular, angles subtended on the same arc. Okay, it turns out that you can look at this in several ways because of the symmetry of triangles. You can say that the green line segment can act as a chosen unit, in which case the multiplicants are this dark blue line and the purple line or the pink line. Or you can choose the pink line as a unit, and then the multiplicants will be the green and the red, or any one of the others that you please. Now, for example, if let's say this line here was pi and this line here was square root of 2, then the red line would represent the product. And of course, the quotient of the red line and this purple line or pink line would be represented by the blue line, and also the reverse is true also, where we say the red line length divided by the blue line length gives us the product, the quotient, which is this purple line. So I'll put a link to this applet too, and you can study it. So if we look at the actual measures, this 1.2 times this distance here gives you this length here. But now be very careful here. You still have to divide this product by the unit, which is this line here, in order to get this value. So if I had to set this equal to 1 approximately, then it would be exact. Okay, so I'm not going to do that right now, but you can do it. You can play around with this and see that it actually works. And so anyway, so then this times this will give you the red line. Okay, so I'm not going to waste time with that. And now there's a very interesting thing in the book of Elements, book 5, in which Thomas Heath describes proportion, which, by the way, in Greek, the word in Greek for proportion is, as you can see here, it's analogia. Okay, so Thomas Heath doesn't really understand this. He just says it gives the ability to deal with irrational magnitudes, which is quite telling, by the way, that he didn't say irrational numbers, because mainstream academics of today imagine that irrational magnitudes or incommensurable magnitudes are the same as irrational numbers, which is completely false, because a magnitude is not a number. And so Evdoxus of Cnidus, that's how you say it in Greek, was a mathematician who came long before Euclid. And how did he realize this particular fact that Sir Thomas Heath states over here? Because he says it's generally attributed to Evdoxus. So how do you realize these things? He could never have realized the proposition 12 in book 5, which is quite a ways down. Proposition 12, which is what all of the theory of arithmetic and fractions is based on. So one thing I take issue here with Euclid over 2,500 years ago is that he didn't use similar triangles. He should have used similar triangles instead of these silly little line segments which make it hard to understand. But if you look at this applet here, I show you how this all works, because book 5 could have been far better explained using similar triangles, in particular proposition 12, which summarizes all the theory of arithmetic with magnitudes. They can be either commensurable or incommensurable. So if they're commensurable, it means they're describable by rational numbers. If not commensurable, that means there is no number that describes their measure. Okay? So I wanted to share this new perspective, because in my conversation with this poor idiot here, he just doesn't seem to understand that in order to define multiplication, in fact any operation of arithmetic, you have to go back to the magnitudes in geometry, because all those operations in geometry were transferred to algebra using the abstract unit. And for that, I've written this world-class article for you, which explains all these details, okay? Even in terms of how the Greeks derived these concepts. And I also have another famous article, which is called How We Got Numbers, to which I'll place links so that you can read these things at your own convenience. Now, it's pretty telling and pretty shocking that somebody with a master's, but he's not the only one, by the way. There are many like him, even with PhD degrees, and several of them, that do not understand these concepts. They have no clue that the foundation of mathematics is not the garbage known as set theory or group theory. It is the elements of Euclid, okay? And we get everything we know about mathematics and science from the elements, which are based on perfect concepts. So you'll notice that I get very irritated in my response with this poor fool called Zealous Malin, and I don't have time for fools. And so the guy is so clueless, he can't understand that you simply cannot say that AC is equal to A times C in a proof, in a demonstration that you are defining for the operation of multiplication. And so I do it for every operation of arithmetic in how we got numbers. And there's also another wonderful video which you can watch here, which is really written for children, in fact, as well. Complete Theory of Arithmetic and Operations. And, you know, number is the most important concept in mathematics. There is nothing more important than number. And anything that's useful in any scientific, technological, or engineering discipline requires number, which is a name that is given to a measure that describes a magnitude or a size or a quantity, okay? So I'm going to leave you with these thoughts. Please become a subscriber if you aren't a subscriber already. If you haven't downloaded my free ebook, do so, and click like, because you know I have many enemies in the mainstream who are wanting to ensure that you don't get to this information, that you remain ignorant, and that this isn't a conspiracy theory, by the way. It's true. I've had my websites taken down several times, and you'll see the animosity and the vitriol which is directed at me in forums like this one, sci.math. By the way, I am eram semper recta, which means I'm always right. And I am smarter than anybody I know. If anybody else had to say that, yep, they'd probably be a crank, but I'm not a crank. And I know what I'm talking about. And you don't have to believe me. You can read my works and see that I know what I'm talking about, and that the fools in mainstream academia are simply incorrigible creatures, okay? So I'll leave you with that. Until next time, my name is John Gabriel. This is New Calculus Channel. Goodbye.